Let's do problem number 58. Jane, whose mass is 50 kilograms, needs to swing across a river having a width d filled with person-eating crocodiles to save Tarzan from danger. She must swing into a wind exerting constant horizontal force F on a vine having length L and initially making an angle theta with the vertical. Take d equals 50 meters, F equals 110 newtons, L equals 40 meters, and theta equals 50 degrees. A. With what minimum speed must Jane begin her swing to just make it to the other side? B. Once the rescue is complete, Tarzan and Jane must swing back across the river. With what minimum speed must they begin their swing? Assume Tarzan has a mass of 80 kilograms. Let's start by drawing the diagram. This is the vine that Jane is on, and so I'm going to represent Jane as a box, and we're going to call her mass J. That stands for, Jane's mass. And then we're going to draw the path of the vine when Mary Jane swings down to save Tarzan. And I'm going to exaggerate the distance between Mary Jane and Tarzan to make it easier to see. I'm going to represent Tarzan as MT. And so this is the path that Jane takes, is this arc here. And the distance between these two cliffs is D. The vine is L meters long. This angle here, I'm going to call it theta 2. I'm going to call that angle theta 1. And you do have a wind force here. Now that we have our diagram, let's write out our givens. D, the distance between the two cliffs, is 50 meters. The wind force is 110 newtons. The length of the vine is 40 meters. Theta 2 is 50 degrees. Jane's mass is 50 kilograms. And Tarzan's mass is 80 kilograms. So here's how I plan to approach this problem. I'm going to set height equals 0 where Tarzan is. And so, as you can see in the diagram, Mary Jane is this much higher than Tarzan. So Mary Jane has this much potential energy. And so this wind is going to go against Mary Jane when she swings. And this wind force is going to be larger than Mary Jane's potential energy. So this wind work minus the potential energy will be the kinetic energy that Mary Jane needs to swing off this cliff in order to save Tarzan. And with that kinetic energy, we'll be able to find velocity. So in order to do that, first order of business is finding out what exactly is this height. So I'm going to do this by solving these two triangles. You have this triangle here and this triangle there. Let's solve this triangle. So I'm going to draw that out here. And we can, as given by the problem, that's 50 degrees. We know this is 40 meters. Using trig, we can find that this x distance here is going to be 40 sine 50, or 30.64 meters. And using more trig, we can find that here, this distance here, or how tall this triangle is 25, or cosine 50 equals y over 40. Y is 25.71 meters. This is 25.71 meters, and this is 30.64 meters. Now that we know that, let's solve this triangle over here. I'm going to draw that out here. And so you don't know this theta here, you don't know what's theta 1, and you don't really know anything else. But what you do know is that when Jane swings, the length of that vine doesn't change. It may look different in my diagram here, but this L here is very much still the same L over there. It's the same vine. So this is 40 meters. And how can you find this length here? Well, that's why we found X over here, because this is 50 meters. If we take 50 meters minus the length here, we'll get the base of this triangle. So once you take 50 minus 30.64, you get this length to be 19.36 meters. And using Pythagorean theorem, you can find this side here, which is 35 meters. So let's go back to our diagram here. This 35 meters is this triangle. So let's write that on our diagram. Right here, from the top of the triangle to the bottom where Tarzan is, that's going to be 35 meters. From the cliff where Jane is standing on to the top of the vine, this is going to be 25.71 meters. And so 35 minus 25.71 will give you this small h here. So this h turns out to be 9.29 meters. Now you can find out how much potential energy Jane has. But before we do that, I'm going to redraw this part of the diagram here, so to make things a little bit easier to visualize. So here is Jane, and Tarzan is down here. So Jane's up here, Tarzan is here. This distance is 50 meters, is the distance between the two cliffs. And this height here, we just found that to be 9.29 meters. So you may be tempted to find this length, but you actually don't need to, because the problem did state that this wind force is constant and horizontal. So when you want to find the work done by wind, all you need to do is force times the horizontal displacement. So that would be 110 newtons times 50 meters. The work done by the wind is 5,500 joules. Now let's find out how much energy Jane has. Jane is going to have potential energy, or MGH, and that will be 50 kilograms times 9.8 times the height, 9.29. Once you multiply that, you will get 4,552.1 joules. And so the kinetic energy that Jane will need to leave this cliff with will be the resistive wind force, we'll call that work of the wind, minus her potential energy. And so whatever is left over is the amount of kinetic energy she needs to leave this part of the cliff with in order to reach Tarzan. So let's do that. So 1/2 mv squared equals 5,500 joules minus the potential energy that Jane has. And so that turns out to be 947.9 joules of kinetic energy. So let's solve for V. So when you do that, you take the square root, 2 times 947.9, all divided by the mass, which is 50 kilograms. And so when you solve that, put in your calculator, velocity is 6.15 meters per second. So we just found the answer to part A. Jane will need to leave with a minimum speed of 6.15 meters per second off this cliff in order to reach Tarzan. But now part B wants to find out, now that Jane and Tarzan are together, the problem wants to find out how much energy will they need to, what's the speed that they will need to leave that cliff in order to come back. What's the speed? And the key to finding that speed is finding the amount of energy that they will need to get from here to here. And that is not too hard, because now the wind is working in their favor, because the wind is going that way and they will be swinging back up. The wind will be in their favor. And so the total amount of energy that they need to reach here is simply the potential energy that they will both have up there. Tarzan and Jane standing up here, 9.29 meters above zero, that potential energy is the amount of energy they need to give at this point in order to get up there. So since the wind is working in their favor, you will find that energy here, subtract that, the work done by the wind, and that is the amount of kinetic energy that they need. And then with that, you can find velocity. So the total amount of energy, or the, I'm going to call it the amount of potential energy they need, is going to be their masses combined, which is 80 kilograms plus 30 kilograms plus 50 kilograms times the G times h, which is 9.29 meters. And so the amount of energy they need in total is going to be 11835.46 joules. Now what you want to do is subtract the energy or the work done by the wind, because the wind is working in their favor. So once you subtract 5,500 joules, the total amount of energy that they need to give at that point will be 6,335.46 joules. And to find velocity, you do exactly what you did here. So 1/2 mv squared equals this energy. You isolate v, 2 times the energy divided by their total mass, which is 130 kilograms. And once you do that, you'll get velocity equals 9.87 meters per second. That is part B. So when both Tarzan and Jane are standing together on this cliff, they will need to leave or jump off the cliff with 9.87 meters at 9.87 meters per second in order to come back here. And this is how you do problem number 58.